All right. I think it's safe. I think it's safe to attempt to start this review session with a word of prayer. Dear Father, we thank you for this day. Again, Lord, I thank you for the students and help us to use the most of this time, Lord. In your name we pray. Amen. So you asked me about the integral of sine cubed over x cubed from 0 to infinity.
Just like how to set it up.
Huh. Well, I don't know. Let's see here. I think I would look at the integral of e to the probably how to get a sine cubed. Huh. Let's see here. How to go e to the I theta is equal to e to the ni theta. Yeah, I mean, we know that. And that's well, that doesn't help me, does it? I mean, I'm thinking de Moivre's theorem. That's no help. I guess I'm just going to look at sine. I mean, for lack of a better idea, why don't I just look at sine cubed to z over, what was it? Oh, x cubed. So maybe z cubed if we're lucky. Dz. And I mean, huh. Well, that has a removable singularity at 0, doesn't it? I'm debating between trying something like this versus trying something like this, you know. If I did do something like this, right? I don't see why the integral would be anything but 0. I mean, I've got no pole, right? Huh. All right, I understand the problem now. Let me consult a earlier, smarter me. All right. So what I did, oh man. Huh. This is interesting. Let's see here. So I said sine cubed x is that. Well, how did I? What? Whoa. Really? That's sine cubed x? I mean, of course we can work that out. I mean, sine of x is e to the ix plus e to the minus ix divided by 2I, and you cube that thing. And if you think about that, it makes sense that we would get a 3ix term, and it makes sense that we would get why is there, man. Oh, it's the imaginary part of that also, right? Man, I don't know where I'm getting that from. Good night. Where on earth did that come from? All right, well, let me set aside that rather large question mark, like where on earth did I conjure this up from? I mean, I trust that it's probably true. And if you do that, then, so I'm going to look at f of z as 1 over z cubed times that, which is just replacing x with z. Then this will reproduce the sine cubed x over x cubed along the real axis, but we'll need to take the imaginary component to select it. All right. So I mean, I just don't understand why I'm not just looking at, the mysterious thing to me is why don't I just do sine cubed of z like this, and I don't know, there's something I'm missing here about the approach. Let's go on though.
So is there no straightforward way to do it, just like from what you have written over there?
There's always more than one way to do it. The question is this a good way? I still am a little bit intrigued as to how this gets to be non-zero. Because, oh, these exponent e to the z over, like these things, that's interesting. So e to the z over z squared or z cubed or whatever, those have 0 as a pole. So if I look at this kind of residue, I can use the fractional residue to pick up the pole.
The e to the iz has 0 as a pole.
Well, it's not just e to the iz, right? It's got the z cubed out front. So that gives me the pole here. It's just the thing that's messing with my head is this idea that, I don't know, I gravitate towards wanting to do this, right? But that, I mean, well, there's no pole. 0 is removable for this thing.
Is the final answer 0?
So the interesting thing is that somehow sine cubed x over x cubed appears as the imaginary part of this function. And that function is not one having removable poles at 0. It has, in fact, a pole of order 3 at 0, I believe. Yeah, I think this function's holomorphic at 0, right? So this is a pole of order 3. All right, great. And so, so if we take this indented contour and take r going to infinity and let t go to 0, then we're gonna pick up, 4 pieces, right? The Cauchy residue theorem says that you get 0 because there's no poles up in here, but we're going to have that fractional residue from the lower piece, I think. So I said that 1 and 2 in my notation here. This one and that one should combine together to give me the integral from minus infinity to infinity of sine cubed x over sine of x cubed over x cubed, which then I can take half of if I can find some argument that it exists, and that's probably not hard. But and then I take the limit as t goes to 0 and r goes to infinity. Okay, so the outer loop vanishes because we have this estimate. The modulus of f of z is that, which is well, I'm not sure I believe that. I'm not sure I believe this. Because what's the modulus of e to the iz?
The minus 1.
Now here z is equal to what? On the we're on 4, which is z equals to r e to the I theta, right? And so we're looking at the modulus of, e to the I r e to the I theta. How does that work out? Well, that's the modulus of e to the I r times cosine theta plus, maybe it's true, I don't know. I'm just suspicious. And how's that work out? So that gives us what? Right. Oh, but 0 less than or equal to theta less than or equal to pi. So what does that say about sine theta? But my larger point is sine theta would be non-negative, right?
Oh.
So the modulus of e to the iz is like, at worst, e to the minus r. Or maybe at best, it's e to the 0, right? So, okay, I don't think what I have written is true, but nevertheless, I think that you can see that this is, you can prove that this is bounded, in fact, by e to the minus r sine theta divided by r cubed. And what happens as r goes to infinity of e to the minus r sine theta over r cubed? It just goes to 0 because r is going to infinity and e to the minus r is not blowing up, because the sine theta is not negative. Yeah. So I think it's okay, but I think that I may have been laboring under the delusion that Sam called me on earlier, which is to go, oh, that's a 3/4, and that's a 1/4, and that's a 1/2, because it's e to the iz, so the modulus of e to the iz is 1. No, garbage.
It is less than or equal to 1, right?
No. The modulus of e to the iz, it depends on what x and y are.
But over here, no, but like the e to the minus r sine theta, that's
Oh,
never going to be greater than 1.
For this one, yes. I'm just saying in the wild, in the abstract. And that's, I'm assuming, a theorem, which is just not even, it's just not true. The modulus of e to the iz doesn't have to be bounded. It could be, if z is real, yay, but it's just 1. But, okay, so with that fixed, I think you can see that the upper loop can be shown to go to 0 by the ML theorem. And so then the, let's see here. Let's go on here. Whoa. Oh, guys. Do we need all this?
I don't know.
You're,
You asked that question yet.
I mean, we're trying to calculate the residue of the function at 0. So what did I just do? I calculated it full bore direct series calculation. That's what this is. But if you wanted to calculate the residue of that at 0, well, that's z cubed, and that's a function which is analytic at 0. So you just use the residue formula for something over z cubed. What do we have to do? 1 over 2 factorial, f prime prime, evaluated at 0, right? The residue formula. What's the residue? What's the residue if we have like f of, well, if we have g of z over z minus z naught to the m, what did we say that the residue of that was at z naught? Wasn't it? Now I'm a little rusty, guys, but I think it was m factorial, the m minus 1th derivative at z naught of m of g. Was it that? Like if we have the residue of g of z over z minus z naught at z naught, we just do what? It's just that, right? Am I wrong? Assuming that g is holomorphic and doesn't have a 0. Well, even if it did. But am I wrong? My point to you is you can go back and calculate the residue. We don't have to settle that right here, right now, but all I'm doing here, guys, is calculating the residue of f of z at 0. So my point to you is if I call this whole thing g of z, if I call all of this g of z, if I 2 times differentiate it and then plug in 0, that should give me, after dividing by 2, the residue of this function of f at 0.
I think it has the n minus 1 factorial, because before it was z minus
Oh,
1
m.
to the n plus 1, and so that's why it was an m.
Oh, there's an m minus 1 factorial here? Oh, okay, okay. Thank you. That's why I need a formula sheet for the final, personally. But you understand what I'm doing here is just I didn't feel like looking that up, so I thought, it's not that much trouble to write down the series expansions for these guys and just do it, right? And so, in fact, oh, that's interesting. I don't know if I really believe that. I think there's a lot of errors in this solution, but hopefully we get to the right answer. I don't believe for a second that that's a simple pole. That's a pole order 3 if I've ever seen one. It's just that a pole of order 3 can also have a residue, because there can still be a non-trivial coefficient to the reciprocal term. So I'm, that's not quite right there. Oftentimes, I don't ever get student feedback on this, so if I make an error in this part of the course, I don't ever get called on it. So, not much anyway. Well, anyway, this is from like 2010, and this was like at the very end of the semester when this happened, if I remember right. So, okay, anyway, now, then using the fractional residue, the integral along that half circle is minus pi I times 3 over 4. So that was, going back, that's that little circle that's encircling the origin. So it's not interior to the indented half circle. And so, in short, I get this is equal to 3 pi I over 4, and so you can solve. Let's see, what do I say? I think I'm missing a 2 here. Man, there's all kinds of errors in this thing. Look at this. 2, maybe? Yeah, 2. Otherwise, how do I get from this to that, right? And also, I picked off the imaginary component. See that I? The imaginary component. So, I haven't quite shown you a solution because thankfully mine was full of errors, which you need to fix. Woohoo! It's a good thing I didn't do this correctly, right? Otherwise there'd be... Let's go back to the very start for a second. So I guess the point is, in order to use contour integration and residue calculus, we need to have some kind of trouble to get into. Like, there has to be a pull to somehow get our paws on. And I guess maybe if we just calculate sine cubed of x directly, it'll become more clear to us what went on here. Minus 1 over 8i, right? Because this cubed gives me 8 and the minus I. And then I get e to the 3ix minus e to the 2ix, e to the minus ix. I forgot my 3. 3 e to the ix, e to the minus 2ix, that's plus. And then minus e to the minus 3ix. Using the binomial theorem. Thinking of A as being e to the ix and B as being minus e to the minus ix, so I get like an alternating plus minus with a B. It's like B, and then B squared is plus, and then B cubed is minus again. Anyway, clean that up, what do we got? We have e to the 3ix minus 3 e to the what? Ix plus 3 e to the minus ix, and then minus 3 to the minus 3ix, yeah?
For that second line, like right by the screen, is that minus 3ix?
Yeah, minus 3ix. Man, how do you come up with that? That's starting point. I do not understand where that comes from. Jeez. Golly, do you have other questions? We should go on. I'm not going to solve. I'm not going to crack that. I don't. I mean, this is why I allowed you guys to ask me questions about these, because they're awful.
I guess.
It's I mean, like I said, there's solving these is kind of like artistry. There's more than one way.
I guess just like the last four all look related to what we did today. Sort of at the beginning. The ones that all have to be like kind of small numbers, but if you say about them.
Yes, I would be happy to try to say something about those. These contour, yeah, there's a reason I made these worth double. It's because they're a pain in the butt. No doubt about it.
And for problem 89, or for problem 90, is it 5? That's what I got.
Don't want to deprive you guys of the joy of doing that one. Let's see
Well,
here.
I've already done it.
I know, but
Oh, but you have
I don't want to edit this. What problem was that we're talking about?
90. We had a street test today, and I was like, if I do well on this test, I don't have to study for the final. It was a lot harder than the first one. I have to study a lot more to qualify finals. And one of my classes,
Problem what?
90.
What was that one?
It was the one with how many zeros are between 1 and 2 in the test. Modules. Oh, Chekhov's, yeah. And so it's literally a 30
Oh,
space paper that we have to write and then present on 15 minutes on our. Oh, goodness gracious. Yeah, and that was, so I was originally supposed to have geometry, abstract, and then that all in the same day. And then these that we have to do. I was really sad because I'm in this stuff class where, I mean, it is helpful, it's for honors, thesis, whatever. But going to class is just a waste of time, kind of.
yes. The number which you mentioned is correct. Oh, about to plug it in, idiot.
And I never have to go back to the final, it's just presentations. We only got through half of them yesterday. So now we have to come back for our final exam next Thursday at 8 a.m. before abstract.
What? You say you mean to tell me you got to go to something before my abstract final?
Yeah, I
It's
might skip it though.
not cool. Not cool at all. I'm not like the sound of that. Honors, huh? Doesn't sound very honorable at all.
No.
Don't keep you from abstract algebra finals.
Everything I've done in this class is exactly like I would write something for math if I were to write something about math.
Yeah. Yeah. I feel your pain. So, I think you'll agree with me that there are two kinds of contour problems, right? They're the ones which are friendly. The ones which are friendly, they involve a technique that I've showed you. And basically going, oh, I'll change the x to a z and think about a circle or a half circle or whatever. In some sense, the 93 that Sam asked about wasn't that bad. I mean, that one's much easier than the one you guys just asked me about. That one's worse, way worse. Look at the starting point which was required. You really got to twist your head in order to find the thing to integrate, to gain insight into that integral. So I would say a problem like that would, of course, be inappropriate for the final unless I explicitly give you like a lot of guidance, right? I mean, I would have to be like, integrate this function. Look at the imaginary part. What does it tell you? You know, and like, it would require a lot of guidance, that problem, for it to be fair.
And for the final, is it going to have more of this stuff on it, like since we covered since the last test,
It's comprehensive, so it's got to have a little bit of A calculus. It's got to have
Right,
a
but like, is
conformal
it
mapping.
mostly, or a lot of it going to be this, since we haven't had a test over it yet?
Yeah, probably more than. I mean, there will be some of it. Yeah.
A lot
But
of agent notes. You said for that.
yeah, yeah,
Like,
yeah. So which let's see here. So let's try to do the FTC one. Yeah. So we're trying to.
98?
Which one? We can do either one. 98.
Whatever, no, whatever.
We can do 98. So let's look at H3. We define an integral for functions. We want to prove FTC, and I meant FTC II, okay? So FTC II, what's it say? If, df d, let's say zeta, is equal to little f, right? Then the integral from, say, a to b of f of zeta d zeta is equal to big F of B minus big F of A. And here, the zeta, which I will eventually learn how to write, is a three hyperbolic variable. It has the form x plus yj plus zj squared, where j cubed is equal to 1, right? I mean, that's the world in which this problem is happening. And so we'd say big F is a what? An antiderivative for the little f, right? I'm not sure about my aim here, Bethany, so you might need to duck. All right, so now the question is, what's this? So we look, so first of all, the setup of the integral, if we have integral of, man, I'm running empty here. So suppose f is equal to u plus jv plus j squared w. Then when we integrate f d zeta, what's that mean? If we break it out in terms of the differentials, I mean, so you could define it in terms of the parameterization like I mentioned in class, but we could also look at it like this. And formally multiplying this out will give you the proper formula for the three hyperbolic integral. And so what's that? Yeah, we multiply it out. There's going to be a real part, a j part, and a j squared part. Each one has three things. So like the real part is u dx plus, let's see here, j times j squared gives me v dz, w dy, plus j times the integral. I'm going to put this away because otherwise I'm going to be going nuts with, I need more room to write, yeah? So then this is j, so we get v dx, and how do we get the, oh, okay, w dz, u dy, okay, great, I'll take it. All of that times j, of course, and then plus, let me move it past the line here, plus j squared times what? Times the integral. And of course, this is all over that curve C, whatever C we're talking about. And what's that? Well, that's to get j squared, I've got my u dz, right? My v dy. And what else? Yeah, w dx, thank you. Okay. Now we're assuming, let's assume that this f is what? Little f is equal to what? It's the antiderivative of the big F, right? Let me see, it's the derivative of the antiderivative. So we're assuming that little f is equal to, what is it? It's equal to df d zeta. Now, one of the things we learned in A calculus is that if you want to rewrite that in terms of a partial derivative, and that's what we're going to want to do, because we're going to eventually want to descend to just an argument from like calculus 3 at each component, just like we did for the test 2, for the FTC II argument I showed you guys on test 2, same kind of argument. I'm going by analogy to that. Maybe you'll recognize it when we get to the end of it, but this is partial f partial x. Okay? And so if I let f, for lack of imagination, let's let it be big U plus j times big V plus j squared times big W. See, then this is what? This is partial U partial x plus j times partial V partial x plus j squared times partial W partial x. But just to make the correspondence manifest, this partial U partial x is what? In terms of the little f, it's what? Remember, this is equal to U plus jv plus j squared w, little w. In other words, this is little u, this is little v, and this is little w. So we can replace the UVWs over here with partial derivatives with respect to the big UVWs. All right? So this is like integral over C of partial U, partial x, plus partial, dx, yeah? Plus partial V, partial x dv, dz, plus partial W, partial x dy, and so forth, yeah? You get the idea? I don't think you need me to write it all out right now. And then what we can do, I'm just going to focus in on the part that I'm going to pick on just the u term, okay? So over in here, what u term comes with a j? You get a partial u, partial y dy, right? And the j squared, we have a what? Partial u. Oh, why? What am I talking about? Come on. Really? Seriously. What was that? Partial u, partial what? They're all x's, right? They're all x partials. They're all x partials at this point. And so over here we've got partial u, partial x. There's more, of course, right? And over here we got partial u, partial x, what? Dz, yeah. And there's more. So let's collect all of the stuff with u together, right? Is that how I do it? Oh man, I'm not sure that's actually what I want. I want to, Oh, I want to, I want the, that's not what I want to do. So sorry, guys. Let me think through this some more. I'm aiming to have what I want is I ultimately want the integral over c of like du plus j dv plus j squared big dw. I mean, that's my goal, to show that identity, because then I can just use the FTC II to pick off each one of these using just ordinary calculus 3 type integration. Okay, so in order to get this du, for example, I need to convert partial u. I need this. Something really cool happens, right? So like this here. See this one? The question is, what is j partial u partial x equal to? I mean, the Cauchy-Riemann equations say that we can change this to partial u, partial y, right? I mean, that's just like in the complex numbers, we have this, right? I times partial, I times partial f partial x is what? It's partial f partial y, right? Similarly, for three hyperbolic numbers, if we multiply by the corresponding the generator which corresponds to the coordinate, that this is the a Cauchy-Riemann equation. We also have that j squared times partial u partial x is what? See this one, in the same way that j times this converts it to a y, j squared times this converts it to a z, right? Those are the Cauchy-Riemann equations if you go back and dig into it. So that gives me and in the same way you can convert the well, the other ones require a little bit more tinkering, right? Because like the next thing is going to be plus like j times integral over c of partial v partial x dx, right? Plus partial v partial y dy plus partial v partial z dz. And why do we have those terms? Well, partial v partial x dx, that's already present where? That's somewhere in here, right here, right? That's already got the j that we want. How about the dy term? Dy paired with v. Well, dy paired with v, it's in here. I haven't written it down, but it's coming from this.
dy with v is in the j squared.
Oh, to the j squared. I'm an idiot. So, okay, so right. So we have dy. So we have j squared partial v partial x, right? And we want to convert that to j times j partial v partial x, which is what?
Partial v partial y.
Yep. Which is precisely what we want to have this. And then the VZ term, where's that from? Oh, the first one, right? So there you've got So, I mean,
And they just do the same thing wrong, right?
but the first one, you're going to have to use your imagination. You have to put a j cubed there, and then split off 2 of the j's to convert the x derivative to a z, and leave the other j to factor out here. So that kind of thinking is involved. But yeah, after all this is done, you've got dw, and then we have a theorem, which is that the integral of du, if we go from a point A to a point B, is equal to u of b minus u of a. This is here. That's just plain old garden variety, like line integral stuff. I mean, this du is nothing more than integral of. This is a real line integral. I mean, the things that are inside the coefficients of the real part and the j squared, what you're left with, these are real line integrals, and you can use the ordinary garden variety FTC II for line integrals to, yeah.
I'm a little confused about where the DW came
So it's coming,
from. Which is like the same, you just work at the same.
yeah,
DW is just like a representation.
right, so this one, you've got partial w, partial x dx from this piece right here, because it's already got j squared. And over here we've got j, partial w, partial x with z. But if you, so you have j, partial w, partial x is j cubed, partial w, partial x. I'm trying to convert it to a, that what I'm working on came with a what? A dz, so I'm trying to convert that to a z derivative. So I just keep one of my j squareds and use the other j squared to convert the w to like that. And then that would give me this piece. And then the middle piece comes from the other w in here, wherever that was. I guess this one. So to convert the y, I again multiply by j cubed, which is 1, and take the 2 of the j's to convert the x derivative to a y derivative, and then I've got the partial y, partial w, partial y, and that leaves me the dw. But my larger idea here was I thought this would be kind of a fun problem in the sense that it's really that same argument I showed you guys on test 2. Do you know what I'm talking about?
I don't think I chose the answer to that question. I think that's one of the ones where I chose.
Let me make sure that everybody is on the same page here. And let's just look at my test 2 solution ever so briefly and make sure that we are not.
That's also true.
So oh, come on.
I think this looks like something that should also go in the abstract homework because they both have J's.
Ah. So this is exactly the proof I was talking about. We do that, and then it's f dx plus if dy, kind of iffy. And then f is partial x, and I that's minus I partial f partial y. But then when you multiply it out, you get that, which means you get that, which means you get that. Actually, this one, oh man, no! Oh, I did it this way. Ew, I just did it this way, but for a worse problem. Why do I try to do anything on Friday afternoon? This is entirely the stupid way to do it. This is the stupid way to do it. Good grief. I should have left this. I should have left this like this. Then I should have made this step like this. Because then this would have been much, much easier. Right? Now, in my defense, the thing I wrote is, well, more basic and just relying on Calculus 3. Then what do I do? Then I use the I use the vector Cauchy-Riemann equations, which is that this is partial f partial y, this is partial f partial z, and so see at the level of the algebra you have the integral of df over the curve. See, because this is partial f partial x dx. And now what I'm writing on the board right now, this is in the spirit in which I wrote the solution to the test, which I should have been looking at before I went down this garden path. What I showed you was not wrong, but it's just like, if you really look at what we were doing at the components, right? We were just, did you notice that like we keep repeating the argument? So here I'm applying the Cauchy-Riemann equations at the level of vectors. The other ones I was applying the Cauchy-Riemann equations at the level of components. Because, I haven't finished it, obviously. The punchline is, then this is df, and then we know that the integral of df is the difference of f of this start and end, because that was the theorem.
Wait, isn't that what you were trying to show?
Well, yeah. But, yes, but no. See, this is the differential in terms of like calculus 3. This, at the start of it, we started with the integral of df dz, d zeta. So there is a distinction, but I admit that it's easy to lose the distinction, sure. And in some sense, like heuristically, all we're really showing, right, is that the d zeta cancels in some sense.
So then you would plug in this case, like the A.
So admittedly, my first argument I showed you is probably the more responsible one to show you. But if we were to follow the same kind of nonchalant method of calculation as in test 2, then you could do what I did secondly. Do you guys have other questions? No?
As far as like for the final like studying and stuff, like would you recommend primarily looking at like full tests and then like revisions, or?
I would say try to see what went wrong on the test that you took and try to think about, how to fix whatever it is that went wrong on the test. That would be probably my best advice. When I think of the final in here, I'm trying to find my test 1 solution. It's in here somewhere. I guess that's it. No, that's not it. What year am I in?
That was the take home part. Yeah. Our test.
I did post the solution.
No. It is dead. Wait, do you have like cables?
Tried.
Like it's gone. So, we use Cornell. I have money. Yeah, it's way in the pit, but.
So just to take a walk down memory lane briefly. We're almost done. So, you guys were like floundering around on this like basic arithmetic stuff. People lost all kinds of points on the basic logarithm and argument stuff at the start of the course, needlessly so, right? So don't let that happen on the final. Like, go back and fix the argument, be able to. So in short, yeah, I would recommend studying the tests. Not that I necessarily ask test questions literally again, but I do try to keep the test in mind as I construct the final course. And
So like focus on the test more than the missions. And besides like the missions that came after the last test, that would be like I'm assuming
right,
representation.
I think that's fair, but I mean, I should have a problem. I mean, I should test on Roche's theorem. I should test on residue calculus, right? I would say residue calculus has supplanted Cauchy's integral formula in terms of its importance. And the A calculus is not a big part of it either. That's like, there's going to be a token question or something, but I don't think that's the focus of the test at all.
I like the ones where you have to count the zeros.
Yeah, those are neat, and they're really, I think, given the amount of time I spent on the Mobius transformations, I would be surprised if I didn't ask find the map which maps one region to another using the distinct triple idea, because some things, I don't know if I ever successfully asked a good test question about that, but I obviously should have, if I haven't already.
There was a choice and only Sam chose the die.
What's that?
There was the one where there was the choice and only Sam chose the die.
Ah, yes. I would probably force the choice on the final, is a likely event.
Like we get to pick.
Yeah.
The other one was so much easier. I don't know why you chose that one.
But who knows? Maybe I'll even make a short final. Who knows? Stranger things have happened. But Jonathan is lobbying for a take-home part to the final. So
When will we take it home?
after the final, of course.
But we leave, right? Exactly. That's his point.
Take home forever.
You guys.
Take home and don't bring it back.
For your own benefit.
So you're leaving town. You're like, my final's done. You're like in the air,
Yeah.
on the road.
Out of sight.
Driving home doing that.
You're mole people. You're going to tunnel home. I mean, what is it? I don't know. But
That's what I'm
not many. Not many of us are like.
Less traffic.
Not. We can't all
What
be.
would be a group final? That would be so much fun.
We can't all be Elon Musk, right? I mean. Okay. Anyway, I should stop. I hope that I was moderately helpful today. I don't know.